Hi, in this video we are going to prove that omega, the space of the differentials, as a vector space over F has dimension 1. This is something we skipped in the physical lectures to save some time. Right, so that's the statement that we want to prove, that the dimension of omega as an F vector space is 1. There is some information in the slides about how you can think of omega as actual kind of differentials rather than like abstract veil differentials. But I skipped it during the lecture, and so you better kind of just ignore those parts in the notes. And you can go to chapter 4, I think, in Stichtenov's book, which elaborates on that. Anyhow, so how would you prove that omega has a dimension 1 as an F vector space? So what you want to do is you want to take any two differentials, or non-zero differentials at least, and you want to prove that there is some x such that omega 2 is x times omega 1. But it's essentially a line over F. And technically omega 1 and omega 2 are in omega for their own reasons. So omega 1 is because it vanishes from some lambda space corresponding to some divisor, and omega 2 corresponding to another divisor, maybe A and B. Right? So maybe omega 1 is here, and omega 2 is in omega B. But because the sum of the omegas is always contains, not equal, but contains in the omega of the minimum divisor, you can just take the minimum divisor and for simplicity, just assume that both of these differentials live in the same, in the omega of the same divisor, which is the minimum of maybe the initial divisors that you started with. And from here on, we are going to denote it by B. So from here on, we are going to assume that omega 1 and omega 2 are in omega of B for some divisor B. Okay, so for the proof, we are going to use a kind of a dummy divisor A. So the things we will need from this divisor, the following. So we'll take it to be a negative divisor, any negative divisor, and we will take its degree, which is denoted by D, to be some small enough number. It's going to be like, at the end of the day, it's going to be something like -5G or something. G is the genus. But think of D, the degree of the divisor, which note is negative, as a sufficiently small number. And also that A is smaller than 0. Now, because A is smaller than 0, because smaller than the 0 divisor, that is, then we know that this means that the dimension is 0, the dimension of A as a K vector space, or the Riemann-Roch space corresponding to A as a K vector space is 0, right? This is something we proved and used also in analyzing Gopa codes. So this means that for a sufficiently large minus D, or D in absolute value, because again, recall D is negative, we have the delta A, which is just the dimension of omega A as a K vector space, not F vector space, is, if you remember, it's G minus 1 minus the deficiency, deg A minus dim A. This is something we proved in the previous in the lectures. And the dimension of A is 0. And the degree of A is D, so you're left with G minus 1 minus D. Right, that's D and that's 0. And once D is like at least 2 or 3 or something like that, you can be sure that this number is strictly positive. Right, because G minus 1 technically could be -1, but then if D is at least at most -2, then this is at least 1 or something. So the first requirement for D is that it's some small constant, sufficiently small constant, so that this thing is, this expression, which is the dimension of this thing, is strictly positive. Soon we are going to require more from D, but that's as a starters. Okay. Now, with this in mind, we're going to define two maps from F to omega, from the functions we have to the omega space. And the mapping is as follows. So you take a function and you output the differential x times omega 1, and in the other case, x times omega 2. So you have two maps. Right, so these are functions, but these are really more than just functions. These are k-linear maps, kind of obviously, and they're also injective because you can invert, right? You can look at x inverse. I mean, the only thing that goes to 0 is when x is 0. And moreover, if you restrict this map to the Riemann-Roch space of B minus A for each of the i's. So each of these two maps you can restrict it to this Riemann-Roch space. What I'm claiming is that you will end up in this range in omega of A. Namely, any element, any function x that sits here, the differentials that you get, x times omega 1 and x times omega 2, will live in omega of A. And to see this, just know that if x is in this domain, the restricted domain, then this means that x, the principal divisor of x plus b minus a is non-negative, or the principal divisor of x plus b is at least the divisor a. And so this means that x times omega I for each of these two i's, well, omega I sits in omega b, if you remember, that's how we chose b, as the common divisors that contains both omegas. So this, the output of the map sits in this set, but if you remember, this set is also a K-vector space. It's omega of b shifted by the principal divisor of x. That's one of the properties that we listed during the lecture. And because x plus b is at least a, then the omega reverses this direction, right? So omega of a bigger divisor is contained in omega of a smaller divisor, because the bigger the divisor, the more constraints you have. You have to vanish on a bigger set. And indeed, that's what we wanted, right? X times omega I is in omega of A. And this is for the two i's. Okay. Now, by Riemann's theorem, we know that if you look at this expression, so this inequality, so the degree of the divisor B minus A minus its dimension, as any divisor, is at most the genus minus 1. That's Riemann's theorem. And just listing what we have, so the degree of B minus A is just the degree of B minus the degree of A, so that's a minus D here. And recall, minus D is actually a large number, because D is a small negative number. So it's a negative number that's large in absolute value. So you can think of it as the absolute value of D if you want, same thing. So that's this. And then you subtract the dimension of B minus A, but because of what we just said, that this map is a injective K-linear map, we know that the image of Ti is precisely the dimension of the domain. It's precisely the dimension of this Riemann-Roch space. So the dimension of this divisor, which is the dimension of the corresponding Riemann-Roch space as a K-vector space, is the dimension of the image of Ti. Okay, so if we'll take absolute value of D to be large enough, then what do we get? So we get the dimension of the image of Ti. Well, if you look at this and just move things around, you move this to the left and the G minus 1 to the right, then you get that the dimension of the image of Ti for each of the i's is at least minus D plus the degree of B, and then minus G plus 1. Now, the way you should think about it, this is a very big number that's independent of these other numbers, right? Because the genus and B are fixed before you choose the divisor A, which has the degree minus D. So you know this, and then you can choose the D. So think of this as constant, and this is a number, a large number as you wish. Then because of that, you can always take minus D to be large enough so that this inequality holds. Right, because you only require that minus D. Yeah, it's very simple. So you want that minus D plus, let's call this C, that's a constant, is at least minus D over 2, not these two, plus some other constant, depending only on G and so forth. So, and again, minus D, you should think of it as an absolute value of D, really. So what you need is that D over 2 in absolute value is larger than some constant. This could be negative, so it's actually maybe a big constant, but some constant. And so you can always choose D to have this, to satisfy this inequality. Okay. And this expression, why did we wanted that to be larger than this expression, strictly larger? Because this G minus 1 minus D I claim is precisely delta A. indeed, delta A by definition is G minus 1 minus the deficiency of A, and the dimension of A is 0, and the degree is D. So that's exactly the G minus 1 minus D that you see here. Right? So the dimension of the images of these two maps are strictly larger than half the dimension of omega A. So that's what I'm saying. So delta A is the dimension of omega A, and we have these two maps, and both of them has image which is strictly larger than the dimension, than half the dimension of this space. And recall, by the way, initially kind of we said that this dimension is strictly positive, so there's something there. So these numbers are non-zero, so it's a half of a number which is non-zero. So this means that these two subspaces intersect non-trivially, right? You know, it's a dimension 4 subspace, and each of them has dimension, the image has dimension at least 3 or something. So what does it mean? It means that there is a, like a, you know, kind of a pigeonhole principle. There is a x1 and x2 in non-zero functions, so that x1 omega 1 is x2 omega 2, right? Because there is a point in omega of A that is attained from both of them. So some product, there is some product of omega 1, some you can take, maybe in this case we denoted by x1, and some way to map omega 2 to get to the same number, the same differential. So x omega 1 equals x omega 2, x1 omega 1 equals x2 omega 2, which concludes the proof, right? We wanted to prove that there is an x, you can divide by x2 or something, and then you get it. Omega 2 is some number, some function, x1 over x2 times omega 1. Yeah, so that's about it. Good. So what we proved just now is that the dimension of this of the omegas of differential as a subspace over F is 1. And it has something to do with the fact that when you differentiate, you can always differentiate with respect to another function. So it's like the d's that I'm kind of not talking about. You can always express dx in terms of dy. These are the differentials up to some function, and this is the function that physicists like to think about. This is some function in the space F, the field F. Okay.